What happened to you? You're supposed to be waiting for the class.
Hello.
Yeah, supposed to be waiting for the class, not me waiting for you.
Sorry, just 2 minutes.
Cannot give you break. Give you break, you run away somewhere. Okay, let's carry on.
Yeah.
Last topic. The nucleus, radioactivity, nuclear reaction. Right, page 260. Nucleus, describe the discovery of protons and neutrons. Experimental details are not required. Explain mass defect, binding energy. Use the formula for mass energy equivalent. Delta E equals to delta mc squared. Relate and use the unit, atomic mass unit and electron volt. Sketch and interpret the graph of binding energy per nucleon, again nucleon number. Okay, know where your, sorry, right? Value of constant. These are the things that we will be using. The one, atomic mass unit, unified atomic mass unit, rest mass of proton, rest mass of electron, speed of light. Okay, I will tend to go a bit further, describe the discovery of proton and neutron. Okay, the basic idea is John Newton, atomic theory. Right? During his time, all matter is made out of individual particles called atoms, which cannot be created or destroyed. Atoms of the same element have identical mass and physical properties. Compounds are combination of atoms of 22 or more different elements. All chemical reactions involve rearrangement of the atoms. Okay, so we picture the atom as small, very tiny. You can divide it until very small bit. That's the atom. That's during his time. And just to review, right, this is your Millikan's oil drop experiment to determine the charge on the oil drop. To show that charge is quantized, that means E is the smallest charge. You got 2 charge, 2 electron charge, 3 electron charge, 4 electron charge. When the charge is stationary, that one, you got electric field going up, the weight of the oil drop going down. So that balance each other. Then from there, we can calculate the charge on the oil drop. Right? That's how we determine the charge on the electron. Right? That's the mass of the electron. That's the potential difference. Right? That's your second term work. And to determine the specific charge, right? Charge to mass ratio, we have an evacuated tube. Right? This whole thing is an evacuated tube, where the electron are deflected by the electromagnetic field here, and we see on the screen here, spot there. That is your same. This your right, low power supply. Heat up the cathode, then electron is ejected. Then this is your anode and cathode. There's an accelerating voltage. There's an X-ray tube accelerate the electron, and then the kinetic energy of electron is given by EV work done equals to kinetic energy. Then at the electric, when right, you first switch off the electric field and magnetic field, you see where the electron hit the screen, that's your point P. Then after that, you turn your electric field on, it will get deflected. Then you turn on the magnetic field, either one of them. And then you adjust until it come back to there. And then from there, your electric force equal magnetic force, we get this formula. Right? Adjust E and B so that the spot returns to P. Note the E and B value. So fluorescent screen, that's your fluorescent screen. Electron falling on the screen, give a bright spot. So P is where the Electric field is 0. Magnetic field is also 0. How do we derive? From this equation, take the M down, take the V down, we get this equation. And then from here, that V there, replace here, we get this equation. Okay, can review yourself. And so that's how we and that's how we calculate our charge to mass ratio. And then since we know the charge, you can calculate the mass. Origin of electron, when an electric discharge, right? That's your discharge tube connected to vacuum pump with one low air pressure here. When an electric discharge is passed through a gas at low pressure, there's your cathode, there's your anode, there's your fluorescent screen, gas at low pressure. The cathode consists of cathode ray consists of string of high-speed electron. Right? Basically, the cathode and anode, the anode will accelerate the electron that's present in the gas there. Right? No matter how low the pressure, there will be radiation from outside. It will ionize that. Then the anode will accelerate the electron. And the electron will pass through the hole there. When the fast-moving electrons strike the atoms or molecules of the gas present in the discharge tube, they remove one or more electrons from the neutral atom or molecule. So electron will hit the gas inside here, causing ionization. So it produces positive ions and then electron. So it allows the electron to pass through the hole and cause a fluorescent, cause a spot there where the electron hit the screen. Then we can learn about thus we can learn the property of the electron, and then we can analyze the electron and find the mass of the electron. Okay, origin of positive ray. Same. Instead of making right, now we make holes in the cathode. Right, thus positive ions of gas are formed. The ions which move towards the percolated cathode get midway in the tube and consist of positive ray moving through the percolated cathode. So where you can study electron, then the next part is you want to have holes made in the cathode and then see what happens. Then you can find the positive ions will hit the fluorescent screen here. And then you know that there's some positive ray, right? We call it anode ray or canal ray. Positive charge canal ray or anode ray was discovered by E. Gonstein in 1886. He performed the same experiment performed by J.J. Constant by use percolated cathode. Right? That one, he make a whole cathode, but Thomson used percolated anode. You can get the electron here. You want the positive ion to be here. Okay, so J.J. Thomson determine the electron. So Gonstein worked on the positive ray. He found that on passing an electric discharge through a gas under reduced pressure, ray contain positive particle move towards the cathode. This is a cathode. So of course he made holes in the cathode. As they appear to rise from the anode, they are called anode ray or canal ray. They are found to contain positively charged. Right? The gas will have different ions, so that's why it's harder to determine. Not like electron. Electron, there's only one electron there, one electron charge there or two electron charge. So this one, when you determine the charge to mass ratio, it's a bit more difficult to spot what is the positive charge. But we can study the properties. They travel in straight line, right? With the canal rays in opposite direction to the cathode ray. They produce fluorescence when incident on zinc sulfide at the back there. Unlike cathode ray, the positive charge particle depend upon the nature of the gas. That means depend on the type of gas you use here. Then you produce your positive ions here. These are simply the positively charged gaseous ions, right? Not the electron, only one type of electron. Charge to mass ratio of the particle is found to depend on the gas on which these originate. Some of the positive charged particles carry a multiple of fundamental unit of electrical charge, right? They lose 2 electrons, so that's why you have 2 positive charge. Behavior of the particle in the magnetic or electric field is opposite that observed for electrons, so we can expect because it's positively charged. So Thomson's idea, model 1906, he explained with the cathode ray tube, show that all atoms contain tiny negatively charged subatomic particle or electron. So Thomson's plum pudding, there's a plum pudding of plum pudding model of the atom have negatively charged electron embedded within the positively charged soup. So the other part is the positive charge, and then the electron are the resin there, right? That's how it show you. That's the picture in 1906. Then nuclear model, which you study in your STPM, Rutherford's coil. Right? This is an evacuated tube, remember? This is your source of alpha particle. From this is your lead. You want a tiny beam there passing through. So you observe most alpha particle travel straight through the foil. This shows that the atom is mostly empty space. Then you can measure some of the, right? Some alpha particles are deflected by small angle. That show you the nucleus is positively charged. Hence, right, where direct collision is reflected back because the gold is heavier than alpha. Occasionally, an alpha, some call it field, or occasionally, an alpha travel back from the foil. So nucleus carries most of the atom's mass. So of course, Rutherford will come to his own model in 1911. Right? Positively charged nucleus, then electron outside, far away from the nucleus. Nuclear model atom, all the atoms' positive charge is concentrated in a small volume called the nucleus of the atom. Most of the atom's mass is concentrated in its nucleus. The electrons surround the nucleus at relatively large distance. Right? That's Rutherford's model. So how did he discover proton? Discovery of proton is credited to Ernest Rutherford, who proved that nucleus of hydrogen atom, there is a proton, is present in the nuclei of all atoms in the year 1917. Right? He think that proton is present in all the nucleus of all the atoms, all the different elements. Based on the conclusion drawn from Goldfoy experiment, Rutherford is credited with the discovery of the atomic nucleus. Okay, how was the proton discovered? There's your incident alpha, there's the nitrogen. Ernest Rutherford observed that his scintillation detector detects hydrogen nuclei when a beam of alpha particle was shot in the air. After investigating further, Rutherford found that these hydrogen nuclei were produced from nitrogen atom present in the atmosphere. He then proceeded to fire beams of alpha particle into pure nitrogen gas and observed that a greater number of hydrogen nuclei were produced. So he tried it out in air. He find that proton is produced. And we can analyze, because proton is a positively charged. You can analyze it using your Millikan's experiment to find the charge, and then you can use your electric field, magnetic field to determine the charge to mass ratio. So of course, when you do in air, you cannot say nitrogen alone. It can be oxygen, it can be carbon dioxide. So that's why he has to You have to do the experiment again with pure nitrogen only. Then they can say, you can say truly that alpha collide with nitrogen, produce a proton and oxygen. We conclude that the hydrogen nuclide originate from the nitrogen atom, producing the hydrogen nucleus was part of other atoms. So you come to the conclusion that, right, since hydrogen is produced from nitrogen, then we can find that the nucleus of all the atoms will contain hydrogen or proton. So that is his experiment. The experiment was the first reported as a nuclear reaction. This is called nuclear reaction, right? Where the nucleus has changed. There's the original nucleus, there's the final nucleus, there's a product that's emitted, right? There's the equation. We will write into the equation later on. Hydrogen nucleus was later named proton and recognized as one of the building blocks of atomic nucleus. Right? That means proton make up the nucleus. Nucleus contains number of protons, 1, 2, 3, or 4. Then it will be considered different type of element. No? Then we can study the characteristic of proton, positively charged, located in the nucleus. Right? That's the atomic mass unit. No need to memorize. Usually will be given you. That's the mass in kilogram. Mass of one proton is almost equal to the mass of hydrogen atom. Right? Because the mass of electron is negligible compared to mass of proton. Proton carries a charge of same as electron, but it's positive, 1.6 × 10⁻⁻19 coulomb. Right? That's a symbol for hydrogen or proton. All the atoms contain proton. Okay, so that's the idea. There's nothing about neutron in the nucleus, only proton. Of course, there's more question to ask. Right? Nuclear model explain Rutherford's experimental result, but it also raised further question. For example, what were the electron doing in the atom? Right? How to the electron? Won't it be attracted to the positive charge there? How did the electron keep themselves from collapsing? Right? Collapsing means proton and electron combine together. Right? How did the electron keep themselves from collapsing into the nucleus? Since the positive charge, right? The nucleus is positively charged to attract the electron. Right? Luckily, science was ready for the challenge. Physicists such as Niels Bohr continued to design experiments to test the nuclear model of the atom, which eventually evolved into the modern quantum mechanical model. Right? Bohr's model, 1924, where are the electrons and what are they doing? Okay, we always come with question. Then we try to answer our question. If the electrons are orbiting the nucleus, why don't they fall into the nucleus as predicted by classical physics? If we think of a nucleus as the sun, and then the electrons are the planet orbiting around the solar system, right? Around the sun, planet orbiting the sun, same like the nucleus, and then the electron orbiting the nucleus. Then classical physics will tell us, as it orbits, it will emit radiation. Then slowly it will collapse, but it doesn't collapse. How is the internal structure of the atom related to the discrete emission line spectrum produced by emitted element? Right? That's what we studied in the last topic. We see emission line for hydrogen atom, for helium atom. Right? Why? Classical physics will tell us it should be continuous spectrum because continuous energy is being emitted. Bohr addressed this question using a seemingly simple assumption. What if some aspect of atomic structure such as electron, orbit, and energy could only take certain value? Right? That's what we did last topic. We assume that the electron can occupy certain energy level or energy level where the angular momentum is quantized. Okay, Chadwick's discovery of neutron, Rutherford had determined that most of the atom's mass and all the positive charge was held in the small nucleus in the center, and the electrons were held in position at the edge of the atom. The difference between the nuclear mass and the known mass of proton indeed caused a problem. Right? You can measure the nuclear mass. Then you can also build up the atom from the number of proton. Then you find the nuclear mass and the proton mass, they are different. So why is it different? Nuclei were too massive for the number of proton they contain. The mass of proton and the mass of nucleus is completely different. What happened? Right? Rutherford suggests additional or proton electron pair. They never think of neutron. Right? They think of proton and electron joined together, bound together to form extra mass in the nucleus. That's Rutherford's idea. Discovery of neutron. Right? There's your source, polonium source, give out alpha, hit the beryllium, and then neutron is produced. So it passes through paraffin, it produces proton, then you can use a detector to detect it. In the year 1930, the French scientists Frederick Juliet Curie and Irene Juliet Curie found that alpha particles striking beryllium cause it to give off an unknown radiation. Right? This is what it means by unknown radiation. Alpha hitting beryllium, unknown radiation. Difficult to detect, is not charged. This unknown uncharged radiation could knock proton out paraffin. So they put paraffin, it knocked out proton. And these were detected by Geiger-Müller tube. This proton can be detected by Geiger-Müller tube, but we cannot detect the neutron. It has no charge, so we cannot use electric and magnetic field to detect it. Juliet Curie tried to explain the unknown radiation as gamma ray. Right? Explain this neutron as gamma ray. But this ray has no mass. It has no mass. So we have to consider alpha colliding with beryllium, right? Using conservation of momentum. It doesn't make sense. Okay, it must have a mass. Chadwick repeat the experiment using other target material as well as paraffin by considering momentum transfer and the conservation of kinetic energy in the collision between particles. Chadwick concluded that beryllium radiation was a neutral particle that has a mass about 1% more than that of proton. In 1932, he published his proposal for the existence of this new particle, which he called neutron. And in 1935, he was awarded the Nobel Prize for discovery. Okay, so that's how he looks like. British physicist James Chadwick discovered neutron in the year 1932, was awarded the Nobel Prize in physics in 1935 for his discovery. Characteristics of neutron: no charge. They are electrically neutral. They are located in the nucleus of an atom. That's the mass. You need to memorize. It will be given you. You need to calculate. Neutron has nearly the same mass as proton. Okay, atom. Right? Just review your STPM work. What is the nucleus of an atom? Right? Should be able to tell. Nucleus is the tiny. Right? That's a nucleus. Tiny massive center of an atom. It contains the protons and neutrons. Right? That's the nucleus. Approximately size of the atom. That's the approximate size of atom. Right? Nucleus is 10 to the power minus 14. You don't need to know that, but that's roughly for your general knowledge. Okay. Any questions so far? Stop me if you need to ask question. Right? What is a proton? You should be able to tell what is a proton. Positively charged particle find a nucleus. Is the nucleus of the smallest atom, hydrogen. Right? Or we can say it's the nucleus of the hydrogen. Neutron has no charge and is found in the nucleus. That's about the same mass as the proton. What's a nucleon? Any particle found in the nucleus. It can be a proton, it can be a neutron. Okay, just remember, alpha particle scattering experiment tell us that the nucleus is positively charged as well, and a lot of empty space. Okay, what is the charge on the proton? Yep, what should it be? This one.
Charge of proton positive.
Yeah. If we call electron minus E, what is proton?
Positive P.
E, no? Positive E. Neutron, what is the charge on neutron?
Neutral.
0. Relative mass, if electron has relative mass, what is the relative mass of proton? SPM work.
1.
No. 2000 times greater. Right? That's the exact value. Is 2000 times good enough? Neutron also about 2000 times greater. Right? Atomic mass unit, that one will be given you if you are required to do calculation, which you will be using that. Mass of proton is approximately same as neutron. Mass of proton is about 2000 times. Yeah, that one. Don't need to know the exact value. 2000 larger than the mass of electron. That's why when we calculate the nucleus, we don't bother about the mass of electron. Representing the nucleus, right? X is the chemical formula, chemical symbol. A is the mass or nuclear number. Z is the proton or atomic number. Right? That's an example for carbon. Some author write this way. Mass or nuclear number A is the total number of nucleons in the nucleus. Proton and neutron add together. A major characteristic of an atom is the atomic number or proton number Z, which is defined as the number of proton. Neutron number N is the number of neutron in the nucleus of an atom. So N plus Z equals to your A. Right? Chemical properties of the atom is determined by your Z, atomic number. Number of proton in an atom is constant. Right? A particular element. Number of proton is constant. And different atom has different number of proton. In a neutral atom, the number of proton equals the number of electron. Isotopes. What's an isotope? An atom with the same atomic number, same Z, but different atomic mass, called isotope. Isotopes have identical chemical properties, yet have different physical properties. That means different mass, like this isotope of hydrogen. Right? One proton, one proton, one proton, but it can have different number of neutron. So you have different mass. For example, there are 3 isotopes of hydrogen. 2 of these isotopes are stable. No. Stable means not radioactive, but tritium, this one. 1 proton and 2 neutron. Red is a proton, gray is a neutron. It's unstable. Most elements have stable isotopes. Radioactive isotopes can also be created for many elements. Right? We just send charged particle into the nucleus or neutron into the nucleus to produce radioactive isotope. So these are the different isotopes for this one for hydrogen, this one for helium, this one is for lithium. Okay, this is for your review. Lithium has 2 neutron. Right? These are your isotopes of carbon. This is carbon 12, it's carbon 14, 6 the same, Z is the same. Total number of nucleons, proton and neutron together in an atom is the atomic mass number. The symbol A is denoted by symbol A. So we have more or less completed revising your STPM work. Okay, this one can find in your formula sheet. Same with this one. Mass of proton also. Okay, let's go to your worksheet. I sent to you yesterday. I hope you have downloaded it. Okay, this is last topic. Explain how a line emission spectrum leads to the understanding of existence of discrete energy level in atom. Yep, explain. Yep, give me your answer. Ken? Can or not? Can or not? Right, step by step. No? Each line corresponds to a specific photon or specific wavelength. A photon is emitted when electron changes its energy level. From high energy level, the electron moves to a low energy level. So a photon is given out. And since the energy level is discrete, right? You have discrete and discrete, since the discrete energy changes, so discrete level, that's how you explain. Okay. Any comment? Idea is each line in the emission spectrum represent energy or wavelength that's emitted by the atom. So to obtain this line, the electron must move from a high energy level to a low energy level. Right? The two energy levels are discrete. That's what it means. So that's why you get discrete emission line spectrum. Okay, okay, use your values of constant. What is the mass of proton? Go and find the mass of proton for me. Ken?
Rest mass of proton 1.67 times 10 to the power -27.
Should be able to find it from your value of constant.
Yeah.
Charge of proton? Charge of proton? Yep. I'll give you the formula sheet. You should have your formula sheet.
1.6 times 10 to the power of -19. Positive.
Yep. Should be able to calculate, should be able to find that from your value of constant. Okay, electron is a negatively charged particle of the atom found in an electron cloud. What is the rest mass?
9.11 times 10 to the power -31.
Okay, good. What is the charge?
-1.60 times 10 to the power -19.
Okay, same. I said you put a negative sign there, but usually we don't bother about the negative sign in calculation. What is a neutron? Yeah. Where's a neutron?
Neutron is inside the atom, the nucleus.
Where got atom? Neutron has no charge. Describe it has no
Found in the
charge.
nucleus.
Where is it found? It's found in the nucleus. That's the same mass as a roughly the same mass as a proton. Rest mass of neutron? Right, about there. Roughly the same as a proton. Right, slightly heavier. Right, compare the table. You should be able to fill up. Just now we have more or less done already. Right? That's your E minus E. That's your E. That's your 0. And there's 1. That's about 2000. And then if that is your 1, that's also about 1. That's about, okay, that's how you derive. What does A represent? Yep, I'm reviewing you what we study. A represent what? Your SPM work. We just learn it. Your book doesn't I think your book don't have it. Right? You assume you have known from your SPM, but they have calculation based on it. Yep. What do you call A? Sleeping in class,
A number of proton and electron.
Number of proton and neutron. Right? Mass number. What is that?
Number of proton or electron.
Where got electron?
Number of proton.
Or number of electron also can.
That's why I said.
Tell the number of neutron in the nucleus. You got A, you got Z. How do you represent your number of neutron in terms of A and Z?
A minus Z.
Good. A minus Z, that's all. Okay, state the number of proton, neutron, and electron in aluminum.
Proton 13, electron 13, neutron 14.
Okay, good. This one, your SPM book, you must know. Give an example of an isotope of aluminum.
2813 Al.
Okay, 2813 or 2613 also can. What's the mass of an atom of aluminum in kilogram?
9.11 times 10 to the power negative 31.
No lah, aluminium lah. Aluminium, you must be able to read that 27 nucleon. 10 times atomic mass unit. Right? This is not an isotope. Remember 14, it should be 13. Right? 27 atomic mass unit, roughly there. If it's not given, 10 times your atomic mass unit, get the answer. Okay? Any comment?
No.
What is this symbol for?
Electron.
This one?
Neutron, proton, alpha.
Okay, good. What is the nucleus of an atom?
The combination of proton and neutron.
No lah, I asked you about the atom, you must be able to describe. It's the tiny but massive center part of an atom. It contains a proton and neutron. Not only say it contains proton and neutron, you must tell where in the atom. It's a nucleus. It's a tiny, massive center part of the atom. Right? Size is not important to you lah. Okay, let's go to binding energy. Okay, that's why we have gone over that.
برقد الأمي مش ما أخلي واحد يهينون اللي بصير معي دينار بالدنيا.
Hello. In this video, I'm going to talk about nuclear binding energy and mass defect and show you how you calculate the nuclear binding energy for an atom.
Sorry. Forgotten to share.
To talk about nuclear binding energy and mass defect and show you how you calculate the nuclear binding energy for an atom. So firstly, a thought experiment. Imagine this nucleus. This is a nucleus with 2 protons and 2 neutrons. So it is helium, and it's the standard isotope of helium, helium-4. If you wanted to split this nucleus into its constituent parts, you'd need to apply a force to each of the particles. They're bound together by the strong nuclear force. As the amount of work done is equal to force multiplied by distance, adding a force or applying a force and pulling over a distance means supplying energy. It would take energy to break the nucleus apart into its constituents, and binding energy is defined as the amount of energy required to split the nucleons, note protons and neutrons are nucleons, particles in the nucleus, to split the nucleons apart. So it took some energy to pull these particles apart, and by Einstein's famous equation, energy and mass are the same thing. If you supply some energy, you've supplied some mass. And that means if you were to put these two things on some imaginary scales and we could accurately weigh the helium nucleus and the mass of all the constituent parts separately, you would find that the right-hand side is heavier because we had to supply some energy to get to this state, therefore we supplied some mass. The mass of the 4 bits is always heavier than the mass of the particle when it's bound together. So if we consider the mass of all the particles on one side and the mass of the nucleus, we know we can look up the data for the mass of individual protons, and it's slightly bigger than the mass of one atomic mass unit. Don't forget that atomic mass unit is defined as 1/12 of the mass of carbon-12, but an individual proton is slightly heavier than a 1/12 of carbon-12, and that's of course due to this idea of binding energy. The mass of a neutron is ever so slightly heavier as well, and slightly heavier than a proton. So we can add up the mass of all the bits on the right hand side, that's 2 protons and 2 neutrons, and you get 4.03 U atomic mass units. Again, data can provide us with the mass of the helium. This number would have come from mass spectrometry. And knowing the mass of helium and the mass of all the bits, we can work out the mass defect. That's the difference between the two. The mass defect is all the bits subtract the mass of the particle when they're all together. You get a mass defect in U, and you can multiply by this conversion factor because 1 U is equivalent to this many kilograms. That gives us a mass defect in kilograms. Now we know the mass defect, we can work out the binding energy. The binding energy is defined as the energy required to split the nucleons apart. Because energy and mass are the same thing, the amount of mass defect is equivalent to the energy difference. Energy equals mc squared, multiply the mass defect by the speed of light squared. Note standard units for mass are kilograms, and this is the speed of light in meters per second. That gives 4.4 times 10 to the minus 12 joules. That's a very small number, but it's pretty big when you consider this is just for one nucleus. The electron volt unit is a better unit for comparing atomic energies. An electron volt is the energy given to one electron if it's accelerated through 1 volt. And that can be shown to be equivalent to 1.6 times 10 to the minus 19 joules. That's the charge on the electron in coulombs multiplied by 1 volt. So to convert from joules into electron volts, we're going to divide by this number, and that leaves 27.4 times 10 to the 6 electron volts. 10 to the 6 can often be written as million or mega. So 27.4 MeV is the binding energy for a helium-4 nucleus. Now, it's often more convenient to quote the binding energy per nucleon. There are 4 nucleons here, 2 protons and 2 neutrons. And the binding energy per nucleon, therefore, for helium, is 6.8 MeV by these calculations. So on this graph, the binding energy per nucleon of helium-4 is plotted here, and all of the other elements, and in fact isotopes, can be plotted on a similar graph. You'll notice that the average binding energy per nucleon from hydrogen to helium goes up. That means if we were to take hydrogen and join them together, that's a process called fusion, to make helium, the helium would have a greater binding energy per nucleon. And that means that energy would be released in the joining of hydrogen 2 nuclei, for example, into helium. And that process is called nuclear fusion, and it's what happens in stars. Stars can combine elements together under very high temperatures and pressures because these things would push each other apart. And the nucleons would go up the binding energy per nucleon curve, therefore releasing energy. But once you get beyond iron 56, the binding energy per nucleon decreases. That means it's not possible to release energy by fusing together elements heavier than iron. And in fact, stars will only fuse together elements up to iron and release energy. Stars can create the heavier elements up to uranium, but only in a supernova when the star core collapses. And this collapse provides an extra increase in gravitational pressure and an increase in energy, and the energy needed is absorbed by the nucleons, and so they move to a lower binding energy per nucleon state, an average that is for each of the nucleons. It is possible to split heavy elements into lighter elements, and that process is called nuclear fission. In nuclear power stations we can take a fuel like uranium, and uranium-236 will spontaneously fission, split into two fragments, further up the binding energy per nucleon curve. So going up releases energy, going up this way is fission, splitting, and going up this way is fusion, joining. Both of those processes release energy up to iron.
The very first time I saw the cloud monster,
Wow.
wow, that's a monster actually.
This is the biggest clouds we've ever done.
Okay, let's go back. We will take a short more time. Okay, we'll define and calculate binding energy, study the graph of binding energy per nucleon, and then apply the binding energy to nuclear reaction. That's your 25.3. Introduce Q value to tell us whether the reaction is feasible. Application to fission and fusion, which is under here. Relationship between mass and energy. Einstein suggested that energy and mass can be converted from one form to the other, as well as matter as mass. That's your equation. Usually we put a delta M there to show it's a small change in mass, produce a small change in energy. So that's energy in joule. The mass is delta M is in kilogram. C is the speed of light, 3 × 10⁸ meters per second. This one is called Einstein's relation. Law of conservation of energy is now replaced by law of conservation of energy and mass. Or you can think of mass as a form of energy. Total energy and mass is constant. When mass disappears, it appears in energy. Or likewise, when energy disappears, it appears as mass. That's your Einstein's relation. So supplying an object with any form of energy increases its mass. Supply energy to a mass, heating it up, increase its mass. Energy and mass are equivalent. That's interchangeable. Heating and mass increase. Heating an insulated block increases its mass. That's what Einstein's relation tells us. Mass of the moving body increases. Increase in mass is too small. Okay, that's why I asked you to calculate in your worksheet, question number 16, just to get you familiar with the formula and work with the formula and memorize the formula. You can try it out. I'm having a problem. Okay, let's define atomic mass unit. Your SPM work based on carbon 12 scale. What is happening? Carbon 12 has 6 protons and 6 neutrons. Sample of pure carbon 12 are more easier to obtain than pure hydrogen. That's why we use it as a scale. Unit is used to measure mass of proton, neutron, and electron. Is the average mass of a proton and neutron in a nucleus. Not separate, but in a nucleus. Right? There's a mass, don't need to memorize. Right? There's a data for atomic mass unit for electron, proton, and neutron. It usually will be given you. You're required to use it for calculation. Right? Mass of electron in kilogram. Atomic mass unit is convenient to measure mass of atom, nucleus, proton, and neutron. Right? We don't want to always write 10 to the power minus 31 or 10 to the power minus 27 for neutron, for proton and neutron. Right? So remember your atomic mass unit is the average mass of proton and neutron of C12 in the carbon. Normally in calculation, you need to keep the number of significant figure used. You cannot round it off. Right? Example, you round it off for proton and neutron to 3 significant figure. Both of them have the same value. Right? So you must use the same number of significant figure. Only finally, maybe you can round it off to 3. But calculation cannot round it off. Must use the exact number of significant figure given you. Okay, so just to repeat where you find on your value of constant. That's your for A level. Any comments so far? Anything not clear?
So far, okay, sir.
Okay, let's carry on then. Okay, calculate for me. Yeah, using that. Use E equals mc squared. Then after that, convert it to mega electron volt. Your 1 electron volt is 1.6 and 10 to the power minus 19 joule. Okay, U is in kilogram, is in mass. Mega electron volt is energy. So convert your 1 atomic mass unit to kilogram first. Then use E equals mc squared. Can? How many kilogram is that? Yep, what do you get for energy? What do you get for energy?
1.494 times 10 to the power negative 10.
Okay, now convert it to electron volt or mega electron volt. What do you get?
Convert to
Electron volt or mega electron volt? You are supposed to get this answer. Lost my mouth here. This one, if you get this number, you cannot get, then explain why you cannot get. Did you do calculation wrong? Can get? Divide by 1.6 and 10 to the power minus 19. Can or not? Can or not?
Cannot lah, sir.
Just divide only, right? Convert it to electron volt. You divide by 1.6 and 10 to the power 19. That's all. And you get 934 mega electron volt. Why you cannot get 931? Anything wrong? Have I done anything wrong? Have you done anything wrong?
No.
Then why?
Maybe it's the early conversion, I guess, sir.
We use round off figure. Right? We didn't use the exact
We round
value.
off too early.
Okay, we didn't use the exact value for atomic mass unit in kilogram, and the speed of light is not exactly 3. It's 2.99792.458. Then the charge on electron is not 1.6. Right? There's a lot of other significant figure. So that's the reason. But depend on what they give you in exam, you use what is given. No? Okay, this is for your info, just to help you understand why we got binding energy. Electrostatic and gravitational force between nucleons. Nucleons and protons. Nucleons are protons and neutrons. Proton is positively charged, and so their force of repulsion. So proton and proton will repel each other with electrostatic repulsion, and the force is very large. The other force acting on proton is the force of gravity. This force is very weak, right? Because the mass of proton is very small, or mass of neutron is very small. So atomic mass unit we define as 112, the mass of atom of carbon 12. Right? So 12 grams of carbon contains 6.02 times 10 to the power 23 atom. Sorry, should be 2, not 3. Then we can divide. Right? That's how we get our answer for mass of an atom. Then we want to find mass of nucleon or atomic mass unit. Right? There are 12 nucleon in the carbon 12. So average mass of nucleon, right? Is that value there? That value divided by 12. 1.66 not times 10 to the power minus 27 kilogram. Right? So you can think of atomic mass unit is actually the average mass of a nucleon in carbon 12. Okay, electrostatic and gravitational force, just for info only, just to give you some idea. You can calculate out from the mass, the gravitational force is attractive. Proton and proton, repulsive force is 230 Newton. So you can see that the electrostatic force is very much greater than the gravitational force. Okay, based on the calculation of the separation as 10 to the power minus 50 meter, force of gravity is about 1.9 times 10 to the power minus 34 Newton. Electrostatic force is 330 Newton. So you can see that normally we won't bother about gravitational force in nucleus because it's too small, negligible. Neutron have gravity also, gravitational force, right? Neutron attract neutron with gravitational force, but same, it's relatively weak, extremely weak. Neutron has no electrostatic force because it's neutral, no charge. Electrostatic force, most nuclei are stable. For example, helium nucleus is stable. There's 2 proton and 2 neutron. So what hold them together? Because proton and proton will repel each other with the electrostatic force given by that equation, right? Coulomb's law. Proton repel proton with electrostatic force. Electrostatic force between proton and proton are long range, right? That means it acts over long distance. So we introduce the idea of attractive force, right? Nuclear force. Since the nucleus is stable, there's attractive force between the nucleons. This nuclear force must be stronger than the repulsive force between protons. Right? We can call it nucleon force or nuclear force. It's attractive force. It's strong attractive force. Short range, that means it's within the nucleus and then slightly outside the nucleus. Right? As I said, this is for your info to help you understand binding energy. These forces become negligible at separation of more than a few nucleon diameter. Axis between neutrons, nucleons, that means between neutron and neutron, neutron and proton, proton and proton. These forces are independent of the nature of the nucleons. Right? That's what it means by axis between neutron and neutron, proton and proton and neutron. Right? That roughly show you the strength of the nuclear force. Right? That's a nuclear force. At large distance greater than the radius, about 2.3 times the radius. Right? That's your 2.3 there. The attractive force is almost zero. Only repulsive force. That is your repulsive force still acting. This ensures that the nucleons remain as a separate particle. Okay, for small nuclei up to about atomic number 20, which is calcium, the number of neutrons in the nucleus is generally equal to the number of protons. So as you add proton in, you have to add neutron in. No? As you add proton, you have to add neutron in. That's why it's roughly equal. There are some variation in the number of neutrons. Right? Some of them you can add extra neutron, is still stable. That's called isotope. Above atomic number 20, for nucleus to be stable, more neutron than proton are generally needed. Right? The idea is the neutron provide a separation between the proton and proton, no? So that their repulsive force is not too great to make it stable. Neutron help to hold the nucleus together as they exert a nuclear force on other nucleons. Right? They attract the proton, they attract the neutron. So that's the attractive force. Proton and proton will repel each other. They act as a space butter, if you like, between the mutually repelling positive charge of the proton. Okay, binding energy. Electrostatic force and nuclear force together determines whether the nucleus is stable. An unstable nucleus decays to a more stable nucleus. That means it's radioactive if it's unstable. Where nuclear force is present, there must be, if there's, remember, nuclear force is attractive. So if you want to draw the nucleons apart, we must supply energy. Right? Energy is required to separate the nucleons. Just example, positive and negative charge will attract each other. So to separate them, we must supply energy. Right? To do work, pull them apart. Because the force is attractive. So binding energy of a nucleus is a minimum energy required to completely separate. Idea of completely separate means you move it to infinity. The nucleons of the nucleus. Or right, the individual nucleons come together to form the nucleus. Energy release, either one. Larger the binding energy, the greater the attractive nuclear force. Right? So the binding energy is an indication of how strong is the nuclear force in the nucleus. Okay, mass of nucleus. Right? Mass of proton is given. Mass of neutron is given. Right? That's the mass of nucleon. That's the mass of nucleus. Right? That's what individual neutron and proton. That they combine to form the nucleus. Mass of nucleus, mx, is found to be less than the sum of the mass of the nucleons. Right? That nucleons there have heavier mass than the nucleus. A is the mass number, or Z is the proton number. For a nuclide, neutron number is just A minus Z. We are just repeating. right? So we can summarize that. Right? This is the total mass of the nucleons, number of neutron times mass of neutron, number of proton times mass of proton is greater than the mass of nucleus. Okay, that the one show you. That's the total mass of the proton and neutron together. Here, that's the mass of nucleus. When we compare the mass of helium and the total mass of individual nucleons, we find that there is a mass difference. These two mass, there's a mass difference there. We call it a defect lah. That's the idea of mass defect. We call the difference mass defect. Total mass of individual nucleon is greater than the mass of nucleus. So mass defect or mass excess is the difference in mass between the total mass of nucleons in the nucleus and the nucleus. Right? Total mass of the nucleons minus mass of the nucleus. That's your mass defect. Okay, so far? Anything you want to ask?
No.
We will stop in a while. Right? Binding energy, or sometimes called Q value, delta E equals delta mc squared. M is, remember, is kilogram, C is the speed, meter per second. So difference in mass delta M appears as energy released when the nucleus is formed. When the individual nucleons come together, form the nucleus, right? The mass defect is released as energy. And then the conversion of energy to mass to energy. Binding energy per nucleon is defined as the total energy needed to completely separate all the nucleons in the nucleus divided by the number of nucleons. Right? We define another term, binding energy per nucleon, so that we can compare one nucleus, one element with another element. Okay, so that's the binding energy. That's the binding energy of the nucleus or the atom divided by the number of nucleons. So that's the binding energy per nucleon, where A is the mass number. This quantity allows us to compare the stability of the nucleus. Okay, number 10, you can calculate out for me. Yep, calculate the mass defect. Don't bother about the electron. Calculate that there are 2 protons in helium, 2 neutrons in helium. So calculate the total mass of proton, total mass of neutron, then subtract the mass of helium, nucleus. Can get? Should be able to get the value there that I've shown you on the diagram. Can? What do you get? Make sure you check your email. If not, you're wasting your time coming for tuition without your worksheet. Can get or not?
Yeah, can Jen.
What do you get?
0.0305.
Okay. Then convert it to kilogram to find the binding energy. Times 9.31. Sorry. Times 1.66 and 10 to the power minus 27. Or if you are given 931, then use 931 straight away. Okay. And calculate the binding energy per nucleon divided by 4. Right? So you can say that helium is very stable, very high binding energy. Okay or not? Okay or not? I want to finish this part before I stop. Anything that's not clear?
Clear, sir.
Right? So helium nucleus have a binding energy per nucleon of 7.1 mega electron volt, thus very stable. Okay, comparison of atomic and nuclear binding energy is for your info. Don't need to go into much detail. Go very fast. Binding energy is about 2 million times greater than ionization energy. That's the reason why we want to obtain energy from the nucleus. Right? Nuclear reaction, driving force is the loss of mass. Chemical reaction, bond breaking and bond breaking. Nuclear reaction, mass and energy conversion. Chemical reaction, only conservation of mass. Nuclear reaction, energy involved is about 10 mega electron volt. Ionization energy is about 10 electron volt. Usually in nuclear reaction, we produce gamma photon. Chemical reaction, we produce ultraviolet photon. Stability. Similarly, we can calculate the binding energy per nucleon for every element or nucleus and plot a graph of binding energy per nucleon against A. The smaller the binding energy per nucleon, the easier it is to separate the nucleus from its constituent nucleons. 7.1 is quite high for helium. So a stable nucleus is one which is very low probability of decay. Less stable nucleus are more likely to disintegrate, decay. So a useful measure of stability is the binding energy per nucleon. Right? Usually in exam, they give a smooth curve for you. Right? Minor detail they will meet. Right? Like this minor detail. This is helium 4. Right? That one is for your boron. Sorry. Yeah. That one is I think is beryllium. This is helium. And then boron is here. This one is carbon. That one is oxygen. Right? Don't need to go that detail. Uranium 238 is at the back as the last element there. So when the deuterium is here, deuterium is here, right? H21. So we can see the energy value rises rapidly with increasing A. At this part there. Right? At this part there. It start off from almost 0, go back increasing there to about 15 here, about 15 here, then start to increase less, right? Initially very fast. So energy value rises rapidly with increasing mass number A for like nuclei and starts to level off about A equals 15. Then most of it is about 8 there. About 8 there, most of the element. For all atoms except lighter than carbon, it's about 8 mega electron volt. So 8 is quite stable. Then iron, right? 8.8, A equals 60. It has the highest binding energy per nucleon. Right? Remember, the greater the binding energy per nucleon, the greater the work that need to separate. That means it's more stable. They need more energy to separate the nucleons. So for iron or A equals 60, the nuclei is very stable. After EA, after iron, right, the binding energy decreases again to less than 8. Right? So the less binding energy per nucleon, the easier it is to separate the nucleons from inside the nucleus. Right? That's the point to you. Helium has a large binding energy. Right? So if we break up, right, fission is here. That's your fission, where heavier nucleus splits into two lighter one, so that binding energy per nucleon increases. Right? So heavier one here form into two smaller one here. So binding energy increases. So energy is given out. Right? Roughly that. Same fusion, smaller one here. Right? Smaller these two join together to form helium or beryllium. Energy is released when two light nuclei are fused to produce heavier one. Right? Roughly that amount energy depend on which one you produce. Right? If it's two tritium and helium, tritium and deuterium to produce helium, then that is the amount of energy, about 7 point something to minus about 2 point something. Right? So nuclear reaction usually around, we work around here, right? Around here. Right? Goal is about there. Right? So should be able to identify roughly. Okay, I think we have completed. All these are for you to review. Right? We have completed all that. And then right? We have look at that. Chemical bond is your chemistry part. We look at structure, atom, electron. Then we have look at isotope, atomic mass, and atomic number. Neutron and proton. We have look at E equals mc square. So later on, we will look, next topic will be radioactivity, fission and fusion. Okay, I think I won't bother to do for you. I will stop here. Anything you want to ask? Yep. Anything you want to ask? You can do your worksheet 25 for next class.
Monday. Okay, can sir. Thank you.
Anything you want to ask? Anything not clear you want
No,
to
sir.
clarify before we stop?
No, sir. No, sir.
So keen to go back already. So keen want to finish the class already.
Sorry.
So fast want to finish the class already. Don't want to ask question.
No, I don't have any questions here yet.
Okay, then we'll stop here.
Thank you, teacher. Have a good
Okay.
weekend.
Bye-bye.
Bye.